Hi, good evening, everyone, and welcome to our very first International Observe the Moon night here at UCF's Robinson Observatory. And tonight we are being supported by the UCF Library, Department of Physics, and College of Sciences. My name is Jenny, and I am a PhD candidate here in the Planetary Science track at University of Central Florida. And I'm happy to share our love of the moon with all of you tonight. So this evening we're going to be talking a little bit about some of the history of the Apollo missions and research that's been done in the past and research to come in the future, and also take a look at some of the features on the moon and the geology. And so usually we have this event in person at Robinson Observatory, but due to COVID-19, we have made this a virtual event. And since we do not have telescopes set up with cameras, I took this lovely picture here last night of the moon. So if you are in Florida and happened to look up at the moon last night, this is most likely what you would have seen, or something similar. I took this picture with my cell phone camera and the finder scope on a telescope, which is the smaller component that is more like half a binocular, that's used to kind of like help find the telescope. It helps the telescope find whatever object you're trying to observe. So this kind of goes to show that if you have any interest in astrophotography, all you really need is a good cell phone camera and a pair of binoculars. So we are going to be trying to answer questions this evening. Feel free to tweet at UCF Planetary and use the hashtag UCF Moon Night to get an answer. We'll be trying our best to get back to all of you as soon as possible. Also feel free to tweet any of our other supporters, the UCF Library, Department of Physics, Robinson Observatory, and the College of Sciences. If you have any questions about any of those in particular, feel free to ask questions. Also, if you are a part of the AST 2002 class and you are looking for extra credit for this, there is a form in the description of this video. Please do not forget to fill it out. If you do not fill it out, you cannot get extra credit, and that would not be great. There will be 2 code phrases that you will need. The first of which is, the moon is super. So if you're part of the AST 2002 class looking for extra credit, please write down somewhere, the moon is super. And remember that as the first code phrase that you will need for this evening. So first I figured we'd go over a little bit of the structure of the moon and some of the features that we can observe even just by looking up at the moon with no telescope. So the moon was formed about 4.5 billion years ago in an event that we call the Theia impact event. And this is when a Mars-sized object collided with a very young Earth and essentially broke a giant chunk of the Earth off. And so this impact event involved a lot of heat, and it melted a lot of the Earth's surface and sprayed a lot of molten material into space, and this then coalesced into form what we now know as the moon. And because of this formation, we see that the moon has a very similar composition to Earth. And so Earth has a solid iron core, a partially melted outer core and mantle, and then a lithosphere and a crust. And we see something similar with the moon, although it has mostly cooled down to not be melted anymore. But we do see and suspect that there is an iron core, because as all of this molten material formed into one mass, the heavier elements sunk in towards the center and then solidified, and the lighter material stayed out near the surface. And this is kind of how planets cool, is where they start cooling on the outside. So if you imagine you have a toaster strudel, and it pops out of the toaster, sometimes it'll still feel cool on the outside, but if you bite it on the inside, it's molten hot. It's kind of similar to how the moon is, and even if you let your toaster strudel cool over time, chances are it's still probably going to be really hot inside, just because of how it traps the heat, and tends to stay cooler and cool faster on the outside. And so we do see a very wide range of temperatures at the equator of the moon. We tend to see a range between negative 280 degrees Fahrenheit at night and 260 degrees Fahrenheit during the day. This wide variation in temperatures tends to be due to the fact that there is no atmosphere on the moon. So if you think about Earth and global warming, climate change, whatnot, a lot of heat tends to be trapped by our atmosphere. It's kind of like Earth's blanket. But the moon doesn't have something to trap its heat in, and so a lot of any time one side is facing the sun, that side is going to get heated up due to just direct rays from the sun. And it's kind of like not wearing an oven mitt and opening the oven. It tends to be really hot. But then on the flip side, where there's no sun, it's really cold. But if you're like Earth and you have essentially an oven mitt on, when you open the oven or you hold some ice, you really won't feel that temperature difference, because you'll have something insulating you and keeping everything at a steady temperature. So there is gravity on the moon, and it's approximately 17% the gravity of Earth. So it is possible to play golf on the moon and jump around, and it's not like you'll take a step and suddenly fly off. You'll be able to take really big jumping steps, but there is something holding you onto the surface. And at one point, it was thought that the surface of the moon was so fluffy that the astronauts, when they landed, would just sink right through. But this, as we know, is not true. And fun fact, the first actual words when the Apollo astronauts set foot on the moon was actually, "Hey, it's solid. I'm not going to sink through." And this was basically letting all of the people back at NASA know that they are not in any danger of sinking through, as it was thought at the time. And there's a difference in color in different areas. So there's a darker area here and sort of lighter areas. And I'll go into that a bit next. So the lighter areas are known as the lunar highlands. And these areas are essentially large plateaus and mountains that are visible to us as these lighter materials. And part of that is because the material is just a lighter color, but it's also due to the fact that these areas tend to be up higher, and so they aren't in like a basin or a shadow, so when the sun shines on them, they're going to appear more bright. And this surface tends to be older than the darker areas on the moon, and this is due to the fact that in the early stages of moon formation, there was a lot of volcanoes and lava flowing on the surface, and lava tends to flow downhill, and so the lava never really covered these higher plateaus. So we can see that the surface is relatively unaltered. The only real form of alteration on the surface is craters. And this provides a really great cratering record of our solar system because this area is essentially untouched by any other form of weathering. So we don't have lava forming over this region. We don't have any sort of wind erosion or water erosion. This area is essentially just a plain map of the cratering history of our solar system. So the darker areas are called the mare, and this is referring to the fact that they are the lower basin-like regions that then got filled with lava as the moon was still cooling. So there are a lot of lava tubes, essentially holes from the mantle on up, that were flowing with lava, and they'd bring up this lava from near the core and like the partially melted core, and they would flow down into these basins and then cool and form basalt. And basalt tends to be a very dark, hard material, and so when we look at the moon, the dark patches are actually this basalt that has cooled. And one of the most famous of these mare is, you may have heard of it, the Sea of Tranquility. And this is where the first men landed on the moon. And that's kind of in this region here. And they chose this area because the mare tend to not be as cratered, and so it was a lot easier to find a safe landing place in one of the mare, which tend to be flatter, than in the highlands, which are covered in craters. So the moon has a very interesting orbital pattern in that it rotates at the same speed that it orbits the Earth. So in the time that it takes the moon to rotate once, it will have gone around the Earth once. So one day on the moon actually lasts as long as one orbit around the Earth, which is approximately 28 Earth days, or roughly a month. And so this leads us to have a near side and a far side. So the image on the left may look familiar because that's the image that we see when we look at the moon. The image on the right doesn't look like anything we've ever seen, and that's because we never see it when we look up at the sky. That's the side that is always facing away from us, hence it's called the far side. And there's this idea of the dark side of the moon, and originally it was thought that the far side of the moon is the dark side, and people thought this referred to the fact that it was facing away from the sun. When in reality, the fact that it's the far side is the dark side is because when spacecraft fly behind the moon, there tends to be a lack of communication and signal between Earth and that satellite. So for the brief moment when the spacecraft pass back there, there's a communication darkness of some sort. So we can't really communicate back there, but that side may be lit up by the sun. And so we have these different phases of the moon where one side of the moon is always lit up and the other side is always dark. But what we see changes throughout the month just based on where the moon is in its orbit. So when the moon is closer to the sun than the Earth, we tend to only see a little sliver of the sun being lit up, or the moon being lit up by the sun. And as the moon passes behind the Earth, we tend to be able to see more of the area that's lit up and less of the shadowed area. And this also leads to occasional eclipses in which the sun and the moon and the Earth line up perfectly so that for a lunar eclipse, the Earth's shadow blocks out the entire moon, and for a solar eclipse, the moon essentially comes between the Earth and the sun and will block out the sun for a few minutes. So in summary, we really only ever see one side of the moon, and this is because we're tidally locked. So we see the side that has more of the mare, or the younger basaltic lava regions, and then we also see some of the older lunar highlands, which are the lighter portions. So next time you look up at the moon, you can look for this region right here, and that is where the Sea of Tranquility is, and so you can check out where the Apollo astronauts landed. So speaking of the Apollo astronauts, we're going to next hear from Stephanie Eckert, who is a fellow colleague and PhD student here at University of Central Florida, and she's going to be talking a bit about the Apollo missions and some of the history behind space exploration and the exploration of the moon. Also, as a quick reminder, if you have any questions, please tweet at UCF Planetary and use the hashtag UCF Moon Night to get an answer. All right. And here's Stephanie.
Alrighty, let's talk a bit about the history and science of the Apollo program in honor of Observe the Moon Night. So some statistics. Apollo program lasted only a total of 5 years, but there was so much done over such a short amount of time. The three components of Apollo were the launch vehicle, which was the Saturn V rocket, which was famous for being able to carry us beyond low Earth orbit for the first time. In addition, there was the spacecraft itself, which consisted of two components. First, the command module, and then the lunar module. The command module very much served as a mothership where the astronauts would spend most of their time during the mission, and the lunar module is the component of the spacecraft that would descend to the lunar surface with only 2 of the astronauts. So out of the total number of Apollo astronauts, only 12 of them actually walked on the surface of the moon. If we take a look at the timeline of these missions, the first mission that actually went to the moon was Apollo 8, and it didn't land on the moon. It was orbiter. And following that, Apollo 10 did a flyby as well. The first mission that landed humans on the moon was Apollo 11, and infamously the Apollo 13 mission, which was known as a successful failure because the mission had to be aborted due to a burst in the oxygen tank. But over the course of these missions, 6 of them actually completed the goal of landing and returning humans safely. And the total amount that was brought back in terms of moon rocks to Earth was almost 900 pounds at the end of the Apollo program. So there was a lot of science data collected over this short period of time. Here on the left lower corner, I've shown the landing sites. You might notice that a lot of them are in dark areas. Those dark areas are called the lunar mare, and they're called mare which is Latin for sea. And this is because the ancient astronomers actually thought that they were oceans. Also, the lighter colored portions of the surface are called the lunar highlands, and these are the most ancient parts of the surface. The only mission that landed in the highlands was Apollo 16. The rest of the missions landed in the lunar mare, which we'll find out are low-lying impact basins that are filled with basalts that filled up when ancient volcanism led to lava flows. Apollos 8 and 9, famous flybys. On the right there, you'll see perhaps the most famous photograph from Apollo, which is the first Earthrise from lunar orbit. And then the lower left is the launch of Apollo 10. Apollo 11 was the first mission which landed us on the surface, and you'll see on the right in that GIF, there's astronaut Buzz Aldrin with 2 instruments. The first is the laser ranging retroreflector, which was super cool because the astronauts set it up on the moon, and then we were able to point lasers at the moon that would reflect back from these and allow us to measure to supreme accuracy the moon-Earth distance exactly. They also started our collection of moon rocks, bringing back about 50 pounds total. Apollo 12 would continue with the rock collection, but also had a couple cool experiments of its own, 2 of which were the magnometer and the solar wind spectrometer. The magnometer was put there to measure variations in the lunar magnetic field, which what we found out was incredibly weak. Also to check for the existence of a molten core and to look for local magnetic anomalies. The solar wind spectrometer was measuring charged particles at the surface and surface properties, as well as properties of the solar wind itself. Here on the right, I've shown a picture of one of the seismic experiments on the Apollo 14 mission, which seismometers are instruments that measure motions in the ground. And in this experiment, they've generated via small detonations, seismic waves that went through the moon, and they monitored these waves traveling through different parts of the moon. And because seismic velocities vary depending on what type of material they're traveling through. They vary with depth, and that tells us something about the internal structure of the moon, which I'll go into in a bit. Apollo 15 was the first automated vehicle on the moon, which allowed them to traverse much greater distances than before. It also hosted the Solar Wind Composition Experiment, which is an awfully fancy name for a sheet of exposed aluminum shown on the lower left-hand corner. They basically just put this sheet of foil up, and it collected all of the constant stream of plasma and charged particles coming in from the solar wind. They brought it back to Earth for analysis. They also performed a number of studies from lunar orbit, like measuring the lunar gravity field, and also altitude maps of the lunar surface. Apollo 16 had a far ultraviolet camera and spectroscope. The ultraviolet end of the spectrum is actually at shorter wavelengths than we can see, but we can still observe them with scientific instruments, hence what this one was for. It was also noteworthy because they set up the first planetary-based observatory, which was just a 3-inch telescope mounted on a tripod. And finally, Apollo 17 was the last of the Apollo missions to land on the surface. And the experiment I chose from this one is the Lunar Ejecta and Meteorites experiment. This one directly measured the speed, direction, and energy of particles that were impacting the surface. And this is both actual particles and solar wind particles. So to sum up the major science discoveries that were pretty cool from the Apollo mission, first, this one might surprise you a bit, but there were a few, not very many, but there were a couple of scientists who were afraid that the spacecraft and astronauts would sink into a sea of moon dust when they landed. And so that was one of the big discoveries that I put right off the bat. This theory was developed by Tommy Gold, a professor at Cornell, who postulated that dust grains would be levitated by electrostatic forces and accumulate in the low-lying lunar basins and turn them into gigantic dust bowls. 2, the existence of a primitive magma ocean. So early in the moon's history, it was covered by tens of kilometers of magma, tens of kilometers deep. What happened as the magma began to crystallize was that the more dense material sank and settled at the bottom near the mantle. This was the olivine and pyroxene pictured here. And the less dense material rose up to become the crust. Finally, we learned that the moon is ancient, and this one also might sound silly because, of course, the moon is ancient. It's a solar system object, but what I mean by this is the moon is uniquely ancient in that it preserves the first billion years of solar system history, which are not recoverable on the terrestrial planetary surfaces. So, for example, on Earth, we've got plate tectonics, or environmental forces such as erosion and sedimentation. All of these things act to recycle our surfaces. But on the moon, it's actually an ancient record book which details both the meteor impact history and the radiation history from the solar wind of not just the moon Earth system, but of all of the rocky planets. And another cool fact that I'll leave you with is that the youngest rocks that we find on the moon are actually about as old as the oldest rocks that we've collected here on Earth. And just to give you an idea, the youngest rocks on the moon are found in the Maria, the lava basins, which are about 3.2 billion years old, and the oldest are 4.6 billion years old. And on that, thank you for listening and have an excellent Observe the Moon night.
All right, thank you, Stephanie. And next we're going to be hearing about some of the future moon research that will be going on both at UCF and in general. And we'll be hearing about this from UCF's Professor Dr. Carrie Donaldson-Hanna. So, Carrie?
Hi everybody, and welcome to International Observe the Moon Night at University of Central Florida. My name is Dr. Carrie Donaldson-Hanna, and I am an assistant professor within the Department of Physics at UCF, and I'm a planetary geologist whose main research area is the moon. And so tonight I'm really excited to discuss with you and share with you some of the exciting and interesting lunar research going on at UCF. Now, I'm not sure if any of you have heard, but NASA has a major goal to get humans back to the lunar surface by 2024. And this is going to be done with the Artemis program. And so with the Artemis program, NASA will land the first woman and man on the lunar surface, particularly at the south pole of the moon, by 2024. And this is going to be done through a series of missions that you can see in this flow chart from Artemis 1 through Artemis 3. And that Artemis 3 is what will take the crewed mission to the surface. And they're going to do this using innovative technologies to explore more of the lunar surface than we've ever done before. And to do this, they're going to have to collaborate with commercial and international partners, as well as universities like UCF. And this will really enable us all to come together and establish a sustainable exploration of the lunar surface by the end of the next decade. Now, to do this, before we start sending humans back, we needed to send instruments and robots to the surface to really better understand the lunar environment. And so NASA has selected a suite of commercial payload landing services that are going to carry instruments and robots and CubeSats to the lunar surface to really study in detail how we can have humans at the lunar surface doing all these cool experiments and doing all these cool technology demonstrations for long periods of time. And so here are just a few of those commercial landing service providers that will be carrying payloads to the surface in the upcoming decade. Now, we also have other data from the lunar surface that's going to be really vital to mapping and understanding the lunar surface before humans go back. And one of our key orbital missions that will be providing that those maps and the information is the Lunar Reconnaissance Orbiter. And LRO has been in orbit since 2009, and we've been collecting data for over 10 years now, and it's been providing a wealth of knowledge to lunar scientists for a long time. And in doing so, they've mapped the surface at really fine details, understanding boulders, new impact craters, and also making maps of the lunar surface in temperature. And so we now know where the coldest places on the moon are, as well as the hottest places of the moon. And interestingly enough, the poles actually are where the coldest parts of the moon are, which is where we're sending humans back. And one of the key reasons we're sending humans to the south pole of the moon is we want to try to identify areas that are really cold and might contain ice and water so that it can be used as a resource for future exploration. And so LRO has been really vital in giving us that first initial step of identifying where those regions of interest would be. In 2024, we'll have the Lunar Trailblazer in orbit, and it has more high spatial resolution spectrometers on board that will allow us to map temperature as well as water and water ice at higher spatial resolutions than ever before. And it'll really provide and guide where the human exploration and robot exploration needs to go to really study the water and water ice at the lunar surface. And then UCF's also involved in 2 surface missions in the upcoming years. One is the European Space Agency's Prospect mission, which will be landing in the south pole of the moon. It has a drill that will drill 1 meter deep into the lunar regolith and understand the volatiles that are within the lunar regolith and at what abundance they're in the lunar regolith. And so it'll drill down into the surface, extract material, and put it in a mass spectrometer to measure and determine what volatiles are there and how much. And then we're also involved in an instrument payload called L-Series, which is going to have a radiometer or thermal infrared camera on board. And it's going to land on one of those, it's going to get a ride from one of those commercial payload lunar providers called Maston. And it's going to go to the South Pole, and it's going to make temperature maps of the South Pole at really high resolution. So we're talking about scales of centimeters. And so we should be able to see shadows that small rocks and boulders are creating and see the temperatures in those shadows. And we'll also be looking for areas that could potentially be trapping water and water ice. And so you keep hearing me kind of repeat the same thing, that we're looking and exploring where water and ice is, and that really is a strong push with us here at UCF and also with the lunar science community, because we want to understand where this valuable resource is and how much there is to better explore the moon, but also then use it as a resource for further exploration into the solar system like Mars. At UCF, we also are exploring the lunar surface by actually studying lunar samples that have been returned from the lunar surface. And so in my laboratory at the University of Central Florida, we have an environment chamber that we can simulate the near surface conditions of the moon, and we can put samples that we actually collected from the lunar surface by the astronauts during the Apollo mission. And we can look at the heated signature from each of those soils. And then we can compare those to observations that we're getting from the Lunar Reconnaissance Orbiter and kind of ground truth the orbital measurements with our measurements in the lab. And so by combining these wonderful samples that the Apollo astronauts returned, we can start better understanding and better interpreting the data that we're collecting from orbit. Now, at UCF, we're also making our own simulants that are similar to the lunar regolith to better understand how that soil will behave when we have lunar rovers as well as humans at the surface. And so the Exolith Lab, which is part of the Center for Lunar and Asteroid Surface Science program, they are developing and making simulants that we use here at UCF, but we also provide to the community here in the United States, but also internationally. And these simulants are very similar to the lunar regolith, both in the Highlands and in the Mare. And here I'm showing an example of the lunar Highland simulant, and you can zoom in at really, really fine details, and that's what the image is at the very, very bottom, showing how all these little fine grains interact with one another. And how those little fine grains interact with one another is really key for understanding how rovers and drills are going to be able to work in this environment with these types of materials. And so this image up here on the upper right is a really good example of showing how you can take simulant, like what we're building at the University of Central Florida, and use it to better design rovers that are going to be able to maneuver through the lunar regolith. And on the lower right is just showing some of the key people that have been involved at UCF in developing and making these simulants. And several of the students in those pictures are actually undergraduates that are doing this research as well as taking their classes. And so it's one of the many opportunities that students have been involved in to do some cool research here at UCF. And then another key interesting study or research area at the University of Central Florida is understanding how the plumes that come from lunar landers affect the lunar surface. And we know that this is the case even dating back to the Apollo missions. And so here in this image on the bottom left, we can see an image underneath of the lunar lander, and we can see that the engine has actually blasted away all of the finest materials at the surface. And so what's left is more the consolidated material. And above that image is the lunar the Apollo 11 landing site, and this is an image collected by the Lunar Reconnaissance Orbiter, and you can see that around the lunar lander, which is designated by the LM, that there's this kind of bright high albedo region, and this is where the lander has scoured the surface and changed the thermal properties. And you can also see just where the Apollo astronauts' feet have also disturbed the surface in those kind of like darkened regions around the lunar module. And so we know not only that the astronauts can change the behavior of the lunar surface, but clearly the plumes that are coming out of these engines are also affecting the surface. And so we're doing experiments both in the lab and also in microgravity to understand how these plumes engage with the lunar regolith and disturb those surfaces so that we can mitigate that. Because obviously, as this dust plume comes up, it can actually disturb other experiments at the lunar surface. It can disturb astronauts that are working at that surface, but it also alters the surface in a way that makes it not representative. And so then for scientists, it's harder to best characterize what's going on because we've kind of wiped away that evidence. And so it's really key to understand, how this works and also how it'll affect that water ice and that water at the surface when we think about wanting to use that as a resource. And so that's a really big key ongoing area of research. And then finally, another way that we study the moon at UCF is using Arecibo. And so Arecibo is the large radio dish in Puerto Rico that UCF oversees. And we can use Arecibo in two different ways. First, we can use the dish itself to investigate the lunar surface using radar. And in the upper left image, we can see a radar map of Mare Serenitatis and all colors color variations within the basin of Serenitatis. Those variations in color are all related to the amount of titanium in the basaltic flows there. And so with the radar signature, we can really see that. And we can also see the surface roughness. And so really bright areas are regions of the lunar surface that are really rough. And you can tell that by the impact craters that we see around that basin. And then Arecibo also works hand in hand with an experiment on board the Lunar Reconnaissance Orbiter called Mini-RF, to collect signatures at really high spatial scales, to use radar and really look at fine details of the lunar surface. And so it works in conjunction with the Lunar Reconnaissance Orbiter to get these really high spatial resolution maps that we see in the lower right. And so hopefully I've interested you about all the cool lunar research that's going on at UCF. You should definitely check out our website and our Twitter handle to see any new and further exciting developments in our group. And please feel free to send us emails and questions, and certainly during this International Observe the Moon Night, ask questions during the YouTube feed. Thanks, everyone. Bye.
All right, thank you so much, Carrie. Next, we're going to be hearing from one of our supporters, the UCF Library. They've been really instrumental in helping get this event planned and organized, and they have quite a few resources available with regards to planetary science and moon observing. So take it away.
Hi everyone, it's Sandy the Science Librarian here. Thanks so much for joining us for our virtual International Observe the Moon Night event. Sorry we can't all get together. Hope everyone's staying safe and healthy and productive and positive during these challenging COVID times. So I wanted to show you quickly our library resources online found at our guides.ucf, IOMN. It is our research guide that we create every year for basically a listing of our resources and different things both in the library as well as on campus associated to the moon at UCF. So in this guide, normally we bring some of these books with us so that students and families can check them out. So this is a list of our available resources, some different books, some ebooks, as I'm scrolling down here quickly, as well as videos that are available for checkout through the UCF Library. So we have tons of stuff. Here are the ebooks. So if you have access to UCF resources, then you'd be able to click on these links and be able to read these books, which is really great. And then some of our streaming videos or other videos that you can check out, which is the following tab. These are the streaming videos that again are available by the click of a button if you have access to the online UCF libraries. And then at the very bottom, we have some great children's books, which you'll get to have one read to you today. If you go back up to the top, we also have some great UCF astronomy resources that lists all of the different societies and groups on campus that are associated with planetary observations, as well as associated with this particular yearly event with International Observe the Moon Night. So check these out. This is a great resource online that you can peruse and keep track of some great resources. Of course, as well, NASA's Science Earth's Moon website. All right, so the added benefit of being online this year for our virtual International Observe the Moon Night is that we'll get to read a book. So this day, we're actually going to read Darren Farrell's book called Stop Following Me, Moon. On the back, it says here, a giggle out loud tale about the moon, a bear, and learning to share. Grrr. Stop Following Me, Moon by Darren Farrell. Ooh la la. Jackpot. Come to Papa. Mine, all mine. Huh? Hey, stop following me, Moon. My goodness. I said, stop following me, Moon. Get your own food, Moon. This is mine. I'm innocent, Moon. You've got the wrong bear. Who sent you, Moon? Was it Turtle? Eh? Why are you doing this to me, Moon? Just who do you think you are, Moon? You'll never get away with this, Moon. Hey, Moon, look over there. It's Bigfoot. Not cool. Phew! I lost you, Moon. Oh, for the last time. Stop following me, Moon. So long, Moon. Oh no, where did you go, Moon? I can't see anything, Moon. I swear I'll be a nice bear. Please come back, Moon. Moon, is that you? Oh, thank you, Moon. I love you, Moon. Now for a moonlit feast. The end. So thanks for joining me for that little story time, and I hope to see you in the UCF Library soon. Enjoy the rest of the International Observe the Moon Night virtual event, and we hope that you all stay safe and productive during these tough times. Bye, everyone. Take care.
All right, thank you for that fun reading. If you have any other questions, feel free to tweet at the UCF Library, and they will answer any questions that you have. A fun book recommendation brought to you by me is The Rise of the Rocket Girls, and this book is a nonfiction book that goes through kind of the history of women working for NASA and how they contributed to the entire space race and the Apollo missions. So Rise of the Rocket Girls, I highly recommend it. And now for a quick message from SEDS, which is a group at UCF working on research and collaborating with a bunch of different organizations and companies within the Florida region. So here's SEDS.
2, 1, 0. All engine running.
Awesome. Thank you, Seds. That's a lot of really cool and interesting research going on there. And I hope that we all can be a part of it at some point. For now, I'd like to make a quick announcement for the AST 2002 students who are tuning in for extra credit. Do not forget to fill out the extra credit form down below in the description. If you do not fill this out, you will not get the extra credit. And the second and final code phrase that you will be needing for this extra credit is "we are going to the moon." So a reminder, "we are going to the moon" is the second code phrase. Alright, and next a quick word from the UCF Astronomy Society.
Damn, that moon looks beautiful tonight. My name's Adrian Luis and I'm the president of the Astronomy Society. We're a group of UCF students who are interested in space and astronomy. So as you can assume, we do a lot of stuff with telescopes. We set up telescopes for nights under the stars, where we educate UCF students about space. We also do the same with middle schools and elementary schools. We also go to Kennedy Space Center all the time, where we go out and check launches, or we go to tour United Launch Alliance. When we're not in Florida, we're probably out on our out-of-state trip that happens once every year. For example, last year we did a trip that we went to California, and we drove all the way back to Orlando, stopping a bunch of locations on the way, such as SpaceX, James Webb Space Telescope, Johnson Space Center, and a couple others. If we're not doing tours or events or anything like that, we're probably trying to touch space ourselves with our balloon project, which is a project to launch a altitude balloon to 100,000 feet with cameras and science experiments and stuff like that, and basically recover it and get the data back. So if you're interested in our club, please visit us on Facebook at Astronomy Society at UCF, or visit our website at planets.ucf.edu/astroclub. Thank you.
Thank you, Astronomy Society, for that message. And this is going to wrap up our evening for Observe the Moon Night. Once again, a huge thank you to our supporters at the UCF Library, the Department of Physics, Robinson Observatory, and the College of Science. And an even larger thank you to all of you who tuned in for this. All of you are really the people who help keep events like this going. So thank you very much for tuning in, and I hope to see you all back in October for our virtual Nights Under the Stars event, where we will be looking at not only the moon, but Saturn and Jupiter, and potentially some other stars that are visible in October. So thank you again, and go observe the moon.